All right, let's start then. So this is of representation and interpretation, and I hope you weren't hoping for a simple talk today. So what I'm going to talk about to you is hard problems in programming. And as the classic joke goes, that there are two such problems, right? There's cache validation, there's naming things, and there are others. But I would like to argue that it's even off by more than one, because there are a lot of other problems that I often see people struggling with. These are things like string escaping, stuff like time zones, and stuff like character. These are things that we programmers often mess up. And it is my belief that many of the difficulties with these topics are actually related. And in this talk, I would like to show you how and why and how we can reason about these problems. So you should know that this talk is most of all my personal view on this problem. I'm going to tell you some theory, but not all of it is an absolute truth, actually. And it's mostly meant to make you think, this talk. To develop your own views matter. So let's start with the central topic of the talk, which is data. And let's look at some examples of what data looks like. We could have a number, like here. What number is this? 11. If it is decimal. It depends, actually. Because if this is binary, it would be 3. If this is hexadecimal, it would be 17. We don't know, without the knowledge of how we should interpret this data. Let's look at some other data, like a byte we could find in the memory of our programs. What does this byte mean? Well, I've written it down in hexadecimal, right, because of the 0x prefix. That tells us something. But, well, it depends on how we interpret it. If this was a number, it would be 66. This was some character encoded using the ASCII standard. It would be the letter B capitalized. But it could also be part of a byte sequence that encodes a floating point number, or UTF-8 encoding for character. And in that case, we don't know what it is without the other bytes. Another example. We have some JSON data about a person, probably, and its income. So we know that the income is 100,000. But is that per year? Per month? I don't know. Is this US dollars? Is this Zimbabwean dollars? It makes quite a difference. So again, we need to know how to interpret this data to really attach meaning to it. Let's look at another example, a word. For the people among you who mainly speak English, this looks nice. If someone gives you a gift, you get a present. For the people who are used to speaking German, well, their gift means poison. Again, it depends on how you interpret it. Another example. I've written down a prime number for you, a rather large prime number. Or actually, this isn't really a prime number, because somewhere in the middle I replaced one digit with an X. And that has a reason, because if I would write down this full prime number, it actually would be illegal in certain jurisdictions. I don't think the Italians would bother, but in the USA it would be more of a problem. And there's a reason for that. If we would write down this prime number in binary, put that into a file, that file would actually be executable. And that file would implement an algorithm to crack the encoding on DVDs. It's an algorithm called DCSS. And people intentionally invented this prime number to encode this software to demonstrate how crazy it is to, well, make certain programs or certain data illegal. Because there are catalogs of all large prime numbers found online on the internet. This is one of them, because it's one of the largest prime numbers we ever found. So it should be documented there. But it's illegal at the same time. Again, it's just data. What it actually means depends on how we interpret it. So the main thing I want you to take away from this is data has different meaning under different interpretations. Data is just data, and we humans, or the programs we write, give the meaning to the data. So how do we give those meaning to data? what do we have that operates on data? Well, mostly boils down to functions or variations thereof. And I'm originally a mathematician, and so I also look at functions from a mathematical perspective. And let's look at what programming and mathematics have in common when it comes to functions. So most of us were probably taught to think of a function somewhere in high school, something like this. You have a black box which does something, and you put a value in, value x, it goes into the function f, and then out comes the value y. And mathematicians don't care that much about what actually happens within the box. They care more about the types of things that can go in and the types of things that can go out. So mathematicians, they say, well, this function is just not just a function. It's a function defined on a certain domain set, D, which maps to a certain range set, R. So the function f attaches to every element x in the domain in the set D. It attaches a value y from the range set R. And we can think of these sets as class PHP program. And this may look very technical, but if we use types in PHP, we already do something like this. We could have a function which has a parameter x, and we can add a type hint D for the domain to it. And if we add a return type hint, the R, we also say which is its range set. So it's not too different between mathematics and programming. Another example, we could have a function float round that maps to every float, well, its rounded number, which is an integer. So it maps the value 3. It can happen that such maps multiple x values in the domain set to the same value y in the range set. Like we see here, both x1 and x2, if you plug them into the function f, they end up at y. This could happen. And mathematicians call such a function injective. So an injective function is a function for which this can never happen. You cannot find two values x1 and and x2 which map to the same value y. So to get our function round again, round maps the value 3.84 and the value 4.35 to the same, namely 4. So round is not injective. Can we also do this the other way around, you might ask? Can it be that we have one x that we map to two different values, y1 and y2? Is that possible? Well, from a mathematical perspective, we cannot do this. Mathematics only allows pure functions, so those functions always map one x to one y. But in programming, this very often. Those functions are impure. They either depend on randomness or some global or local state. They do I/O over the file system, the network, or they depend on some value of the system clock, for example. If we have a function that returns the current time, well, the output of the function depends on the time we have at the moment. Another thing where some differences arise is if we have one x in the domain set that we cannot really map to one of the values of the range. We just don't have a suitable candidate for that. Well, the mathematicians have quite an easy solution. They just cut that x out of the domain set. So the domain D is now just what it was, except with the x removed. We just cut a hole in the domain. When programming, this is not so easy, because we cannot easily create a type that says, well, this can be any integer number except the number 0 or something. We cannot easily create a type for that. So when programming, we often do something else, and we use exceptions. So instead of mapping those values to the range set, instead we throw an exception. That's something we do differently. So what does this have to do with data and representation and interpretation? Well, we'll see. We can think of these functions and these sets as having a certain level of abstraction. If we take our function round, which maps from a float to an integer, we can say that the set of floats and the set of integers are roughly at the same level of abstraction. They both represent numbers, which we can do calculations with, stuff like that. but the one is not really more abstract than the other one. For other functions, this is not the case. Suppose we have some money value type, and we have a function, serialize money, which converts a money value type into a string representation. Just, well, formats money as a string. We can say that the money class or set is at a higher level of abstraction than the strings. Because, well, our money type is very rich. We can do calculations with money. We can do currency conversion, stuff like that. The string is, well, pretty dumb. We can concatenate them and stuff, but it's not the things we can do with a money type if we want to work with money. We can say that this function actually lowers the level of abstraction. And in the same sense, we could have a function encoded as UTF-16. So we have a string, which is just this string of characters, maybe emoji or something, and we convert that to a byte sequence, which is UTF-16 representation. So again, this lowers the level of abstraction. We had a string that we could see which character was at a certain these strings stuff, and we lower the value of abstraction to byte, which these are examples of what I would like to call a representation. These are functions that translate a higher level concept to a lower level representation. And one characteristic for these functions is that they usually accept all the possible input values. So you have a domain without holes, or they usually don't throw exceptions. We should be able to represent all the possible monetary values as a string if we have a function that serializes money as a string. Ideally, these functions are lossless, so we don't lose any data. We'll come to that later. And essentially, this function just returns the same data as we put into it, just in a different form. We had a money value object, and out came a string that represents the same value. In goes a string, out comes a byte sequence that represents the same string. We could also have functions that raise the level of abstraction. So to reverse the example that we had before, we could also have a function that decodes a certain byte sequence using UTF-16 to a string again. So now we go from a lower level concept, byte sequence, to a higher level concept, string. And we could also have a function that's called parse money, which goes from a string into a higher level concept of money, our value object that we created. These are typical examples of an interpretation. These translate these lower level concepts usually back to a higher level concept. What's typical for these functions is that usually not all input values are supported. Not every sequence is valid UTF-16. Not every string is a valid representation of some monetary value. But again, these functions just return the same data, only in a different form, higher level of abstraction. So these all seems kind of cumbersome, right? Why do we do all this? We usually want to work at a higher level of abstraction. That's the reason why we program in PHP and not in C or even assembly. That's the reason why when PHP doesn't have a high enough level of abstraction, we use frameworks and stuff like that to make it easier on ourselves and work at a higher level of abstraction. Well, we do this because eventually, when we store data, it looks like this. This is our data. It's stored as magnetic grains on a platter. And when we send our data over the network, it looks like this. These electrical pulses or light pulses going to the cable. We cannot send a money object over this cable. We have to represent it all the way down to bytes and then to magnetic grains to be able to send it. So what this often looks like, something like this. We start at a high level of abstraction in our programs because we want to work at a higher level of abstraction. And when transmitting or storing the data, we have to dump it all the way down to these, well, physical quantities, pulses, these magnetic grains, stuff like that. These get sent over the line or put into storage. And then at the other side, or when we pull the data back from storage, we translate it back up, interpret it to the higher level of abstraction that we want to work at. So I was going to tell something about string escaping. And you might wonder what this has to do with it, right? Because you can say string escaping, that's something we do for security. Well, let's look at this. Right? We escape strings for different purposes. We have string escaping for XML using HTML special chars of HTML entities. We could escape strings for usage in a SQL query using MySQL re-escape or something. We could do escaping for LDAP, stuff like that. Let's look at an example for SQL. So we have a script that gets a username from the post data and then executes an SQL query to retrieve the user with that given username. And we have learned that we should do some string escaping, the dbEscape string function here. I don't care which database system I'm using here. Just to protect ourselves in case someone enters some malicious data which might alter our query, like this. If someone would enter the username drop table users with some quotes around it, well, that would actually execute the query to drop our users table, and we don't want that. So that's why we escape our string. But does it necessarily have to be malicious? It might be that our user is named O'Shea. Well, John O'Shea can't help it, his name contains a quote. And there's nothing malicious going on here. It's just, well, this name contains a quote, and we need to be able to put that into an SQL string. That's why we escape it. And it doesn't even have to be direct user input. We also have a case where we retrieve a username from some API. It doesn't matter where it comes from. There's a function, get username using API, and if it returns John O'Shea with the quote in it, we need to escape it to preserve this data properly and generate a valid SQL statement. So in essence, it doesn't matter where this data comes from. It doesn't matter what this data is. It's just we have string. We want to put it in the form that we can use it into an SQL statement. So I'm going to fall back to this. Is this better? All right, then we'll continue this way. So what I want to stress here is that string escaping is, in my opinion, not a security measure. String escaping is just a way of properly representing the data we have for the use case we're facing, right? We have a string, we want to put it in SQL, so we need to represent it in a way that you would represent strings for SQL. So let's look at how this looks in the pictures we had before. We can see escaping as a representation here. So we have a function which is named dbEscapeString, for example, and it goes from the domain string to a range. I didn't really know how to call this. We'll see later. It's quite awkwardly named. But it maps the string John O'Shea to the string John O'Shea with the quote escaped. And why is this range so awkwardly named? Well, our functions which escape something usually do something like this. They get a string as input and they just replace the characters in between. But it would be easier to understand if our string escaping functions actually did something like this. Here, our function just adds the extra quotes around it. So now this is just one valid representation of a string as it would appear in a MySQL query, right? So this makes it easier to understand. And you could now say that it does something like this. We have a function that's called SSQL literal. It takes as input a string, and it returns something that represents a string literal in SQL. And we have a proper representation here. And if we view it this way, we can even make chain escaping a lot easier. If we have some string that we want to use in a JavaScript fragment, then push that JavaScript fragment in HTML, and then store that HTML in a database, well, first we represent the string as a JavaScript string literal. Then the JavaScript string literal is encoded as an HTML attribute value, again, a proper representation, and then we represent that HTML as it would need to appear in an SQL statement. And we just represent all the way down. What can go wrong here? Well, I saw some people doing stuff like this. This is essentially what Magic Quotes did back in the days. So we have a script and all the inputs. At the start of the script, we go over all the user inputs to that script. And for every value in that input,
we already escape it for usage in the database and then escape it for usage in HTML. So why would we do this? At the beginning of the script, we don't even know how this data is going to be used. Are we really going to put it into an SQL query and then put it into HTML? We don't know yet, right? So don't do this. Data is not malicious or something, so we don't have to do anything to make it safe. We just need to look at what use case are we facing. Are we doing something with an SQL query? Well, then at that moment, we represent it for SQL. Are we doing something with an HTML script? Well, then at that moment, we represent it as HTML. And in the same way, I saw stuff like this. There are people who at the beginning of their PHP scripts just go over all the user inputs and look for strings that are malicious, like something like drop table. But if we do so, if I would want to write a blog post about SQL injection or upload these slides, I couldn't, because my request would be refused. The string drop table is not malicious, right? As long as we properly represent our data, there's no need to be scared of it. So this is already one example of stuff that can go wrong here. Let's look at some other ways. We can often do stuff wrong when we represent data. So we have a function that's an implementation of our serialized money that we saw earlier. So this version of serialized money, it converts the monetary concept that is 10 euros to the string €sign space 10. Well, looks okay. We can also have a bad example of such a function, which represents the monetary value of 10 euros just as the string 10. And what's the problem with this? Well, if we also had the monetary value $10, it would get mapped to the same string 10. And that's not directly a problem, except when we are going to, well, store or transmit that, and then at the end we want to interpret the data back to a monetary value, and then our parse money function does not know. Should this 10 be 10 euros? Should this be $10? So we're losing information here. And this is where the injectivity comes in. We need to make sure that the representations are injective, so that two input values can never map to the same output value, and we don't lose data. And of course, this is a contrived example. And you would say, this will never happen to me, right? But still, if we have something like this, we have a date time, which is in the future. It's somewhere in 2022, and we even put a time zone on it. And we represent that as a string, which includes the offset from GMT. So, well, looks okay. We're not losing time zone related information, are we? So, right now, there's some discussion about abolishing daylight saving time. And there are, related to that, some discussions about which country should be in which time zone. I don't know if in 2022, Rome will still have an offset of +1 compared to GMT. So we're losing that information right here. If Rome changes time zone, well, we would have a different outcome here. And this is another a bit artificial example, but if we had a fraction 1/3 and we represent it as a floating point number, there can be a lot of digits, but we still don't know from the letter value whether it was actually exactly 1/3 or something just very close to it. Again, we're losing information. Or we could have some string that contains all these kinds of funny emoji characters and try to encode as ISO 88591, which is also known as the Western European or Latin 1 encoding that people often use. Well, all those characters, all those emoji are not representable in the character set. So I don't really know what will happen here. They will probably get left out or be replaced by some question mark. And again, we're losing information, right? So remember, lossy representations cannot be faithfully reinterpreted. Make sure that your representations are injective, and this will never happen to you. So the other problem, well, we can also mess up when interpreting, right? We could have a function decode from UTF-8 which converts a byte sequence to a string. And there's a certain byte sequence. I didn't write it out. I just put the brackets there to represent it. And when put through the decode from UTF-8 function, it would give the string café. But it doesn't actually look completely like this, because not all byte sequences are valid UTF-8. So actually, this function would only map the byte sequences in the inner circle, in the UTF-8 circle, to a valid string, and all the others would give an exception. But there's a problem. Of all the byte sequences, there are also byte sequences that are valid ISO 88591. And those byte sequences, they overlap with the ones that are valid UTF-8. It's the region in the middle. So if we could just as well, our byte sequence that we have, we can just as well try to interpret it as ISO 88591. And in that case, we would get, well, the string at the top with the funny character signs. At least it's copyrighted. But we get something different than we would want. So the problem is here, right? We have our domain set, and we have two different sets, or we can interpret it as two different sets which overlap. And essentially, well, there's a case of duck typing here. We don't know which one it is, unless we explicitly put it with the data. Well, PHP hopefully has a function for this, at least it says, detect encoding. It detects the character encoding of a string. But how can we do this for such a byte sequence? This byte sequence is both valid UTF-8 and ISO 88591. If we don't know what was meant with this data, we can never detect the encoding. So the actual answer is that detect encoding just tries a number of character sets in a certain sequence and just returns the first one according to which it is valid. But please don't use detect encoding in an attempt to detect the character set of a string. You have to know what character set the string is in, and you can only use it to validate if it's actually valid according to that encoding. So again, the meaning of data comes from our interpretation of it. So if our interpretation of it is wrong, well, we attach a different meaning to the data, not how it was intended. So what can we do to solve these problems? Well, to avoid the misinterpretation, we could try to add some hints to the data about how it should be interpreted and send those along with the data. And there are plenty of examples of this. For example, HTTP headers. When we send an HTTP request or response, we include certain headers to tell the other party, either the server or the client, how this data should be interpreted. We include a content type to say, hey, this is supposed to be text, or hey, this is supposed to be HTML. Please interpret this as HTML. We send a content encoding to say, hey, I want you to interpret this as UTF-8, not as ISO 88591. We send a content language to say, hey, this is meant to be German, not English. I really want to poison you. There are other examples, like the UTF-8 byte order mark. We'll see that in a moment. But there are also examples even of this pattern outside programming. When looking at sheet music, we see just the 5 bars with the symbols on them. And without the symbols at the beginning, indicating what kind of bar this is, we don't know which notes they actually represent. So we include the signs at the beginning as a hint of how we should interpret these symbols. So the byte order mark, right? Essentially, we have a situation like we had before without the byte order mark. If we have UTF-16, we can have that either little endian with the smallest byte at the end, or we can have a big endian with a big byte at the end. And there are byte sequences that are valid according to both, the ones in the center. So we don't know how to interpret those. But if we had the byte order mark, well, these two domains, we pull them apart, right? Because the ones in the left set have one byte order mark, and all the ones on the right have another byte order mark. So they can never overlap, because they have a different byte order mark. So there are no values that are either both in the left set and in the right set. So we separated those domains, so we always have clear how a value can and thus should be interpreted. It is not always possible to include these interpretation hints with the data itself. If that's not the case, we can try to solve this by naming our variables consistently. We could include the intended interpretation into the variable name. So we could have something like message underscore UTF-8 to indicate that it is a message that should be interpreted as UTF-8. We could indicate, we could have username SQL to indicate that it's a username properly represented for usage in an SQL query. We could have title HTML, a title represented for HTML. And that might help us to spot some problems, like this. Here, we send out a header that says the content type is text plain and the char set is ISO 88591. And beneath that, we print out a message in UTF-8. This is clearly wrong. We could have something like this. If we use the underscore SQL suffix consistently, we see that this is a string that's not properly escaped for SQL. So, in essence, we also have an SQL injection vulnerability here, but essentially it's just a misrepresentation. We could also have something like this. We put HTML entities over a string that's already valid HTML. Why are we doing this? This seems like double encoding the string, unless your goal was actually to make an HTML example in an HTML page. Then it's okay. But this allows us to spot those problems. Now, there is something that makes all this a bit harder, because I made a clear distinction between byte sequences and strings at the beginning of this talk. But in PHP, this is not really the case. Let's look at how PHP looks. So we said we had a function encoded as UTF-16, which maps a string to a byte sequence. But PHP says it has a string type, but it's not actually a string type. It's not just a sequence of characters that PHP knows which are the different characters. Actually, PHP's string type is more of a byte array. PHP doesn't know which character set it is. It's just a sequence of bytes. And especially without the multi-byte extension, if you do string operations, you are just doing the operations on the individual bytes. So what it actually looks like is something like this. We have a function encoded as UTF-16, which maps from a string back to strings, which are sort of the best representation of a byte array. So what we don't get is we don't get to raise the level of abstraction, and we still need to work at the lower level of abstraction, which we don't want. Instead, actually, if we work with this, it's almost like every time we need to do something with a string, we use it as if we were interpreting it as a certain encoding. So we interpret this over and over again. It's almost like every time we use a string, we put on some glasses to look at it as if it were UTF-8. So we interpret time and time again, so there's a lot of possibilities to make mistakes, and we don't reach that higher level of abstraction. Because, well, if it's just a byte array, we can also interpret it as if it were UTF-8, and we would get a different string, not the one we intended. So if we want to solve this problem, we need more accurate types. We need to have a real string type, which PHP does not provide for us. Well, we could try to make one ourselves. So let's have a look at how value objects can help us here. So we could create a value object that represents a sequence of bytes that are valid UTF-8. For brevity, I used here the PHP 7.4 typed properties syntax. PHP 7.4 will give you the opportunity to type your properties, which is a nice way to indicate what type of value you intend there. So we have a class that internally, well, it stores the bytes as a string, but due to the private constructor and having named constructors with that, we completely hide the fact that internally we represent those UTF-8 bytes as a string. And in the same way, we can have a class ISO 88591 bytes, which represents a byte sequence that should be valid according to ISO 88591. And again, we hide the way that we represent that internally by using a private constructor along with named constructors. So from the outside, we cannot see how we store those bytes. We just know that this is something that represents a byte sequence. This is valid according to this encoding. And then we could create a class that we, well, will call real string, because this is meant to be a real string type instead of PHP's fake string type. So again, here internally, we choose to store the value of our string as UTF-16, like many programming languages, especially JavaScript, do. And from the outside, we cannot see this again. We have just a function to create such a string from UTF-8, and to obtain the correct internal representation, we convert the UTF-8 to UTF-16 and use that as the internal value. And in the same way, we could have a function that creates such a string from ISO 88591 encoding. We also should be able to represent this value back. So we can also have a function to UTF-8 and to ISO 88591, which again convert the internal representation, which we know is UTF-16, but which is not visible from the outside, to the correct encoding, and then just return a byte sequence according to that encoding. And now comes the fun part, because on this real string, we can now add all those string methods that we actually want, the things we want to do with a string. We could have a method that concatenates two of these real strings without worrying about the character encoding. We know that internally they are both UTF-16. And we can also take a substring, which we can do safely because we know that the string is internally UTF-16. So these are all the higher level string abstractions that we get by working at a higher level of abstraction. So how can we use these types? Well, we could have something like this. If we have one file, file1, which we know to be a string in UTF-8 encoding, well, we can get its contents, say load it into a UTF-8 byte sequence and create a string from that, string 1. We also have a file 2, which we know contains ISO 88591 encoded strings. We load the data from that file, put it into an ISO 88591 bytes class, because, well, then we have a type-safe wrapper around it. And we also can create a string from that. And from that point on, we have a real string type, and all the original character sets don't matter anymore. We can do all kinds of operations on it, higher level, all these higher level string operations that we want to. We can concatenate them, take a substring, for example. And then, at the end of our script, when we want to output this again, well, we convert it back to a byte sequence and convert that to a PHP string, because, well, that's the only thing we can print or echo. Right. So this allows us to work at a higher level of abstraction with no room for misinterpretation after the initial interpretation. So let's look at how this looks graphically. This was the situation that we had. We had the string type, which was actually a byte array, and there's the UTF-8 byte sequences and the ISO 88591 byte sequences, and they overlap. So if we have a value in the middle, we don't know what it is. And by using value types, we separated them to have separate classes, UTF-8 bytes, ISO 88591 bytes, and real string, and no overlap between those. So we always know what is meant with a value and how we should handle that. So in this case, value objects enables us to achieve higher levels of abstraction and thus avoid misinterpretation. But be aware that this is no silver bullet. This comes with considerable overhead. It's quite a lot of work to implement all these type-safe wrappers. It's quite a lot of extra performance costs for all the internal conversions. It takes quite a lot of time to develop something like this and also to work with it. So you should really reserve it for situations where there's a lot of character encoding juggling or stuff like that going on, and you really want to get the types right. Maybe it's something to use for a prototype, to try something out, get a knowledge of how those character sets work, then throw it away and implement it correctly without those type-safe wrappers. So as a recap, we have looked at data, how the meaning of data is not completely defined yet and how we attach meaning to it, how functions, which map from a domain to a range, can increase or lower the level of abstraction, which is essentially an interpretation or representation of those data. We saw how string escaping is actually just proper representation of data, and we saw how we can mess up representation and interpretation, and some ways to solve that by, for example, using interpretation hints. How the string type is actually just a strange hybrid, which make this difficult to work with because we can't raise the level of abstraction, and how we could use value objects in some certain situations to improve that and allow us to gain a higher level of abstraction. But the most important part I want you to take away from this is that the meaning of data is defined by how we interpret it. All those data doesn't have an inherent meaning. All that meaning is assigned by us. That's something to remember and to think about in these situations. Thank you.